All right, we're back. We are examining the Python code for lexical analysis of simple expressions, arithmetic expressions. And last time we went over, of course, the state diagram, and we scattered the code across 4 different files. One of them called the token types, which is just an enumerated type of all the tokens you have, including the end of file token. Okay? And then there was the token.py class, which encapsulated information about a particular token. And that consists of the actual enumerated value, token value, and a value associated with the token, such as the number for an integer token, or the name of the variable for the variable or ID token. Okay. And also this particular token class had a constructor, which we have seen how to use it, and also the string method to convert it to a printable form as a string. And we just had the 2 getters. And also we looked at the lexer.py program. So this is again a class. We create a lexer object out of this. And this is a 2 instance variables. Basically both are working together to keep track of a list of tokens from the input. Okay, and the index is the pointer into the list, and underscore tokens is the actual list of tokens. And this constructor gets the string, such as this one here, as the input, and there's a helper method called tokenize, which takes that string and does the heavy work, heavy lifting for this whole lexer class, and breaks this down into tokens, of course using that state diagram as a template. Okay, and returns the list of tokens here. And then the final method here was lex, which returns one token after another, you see, upon demand, only when requested. And this code was pretty straightforward. I think we looked at that. But you can see it's very systematically written. So if you had to build a lexer for some other language, just a minor change here and there would get you going, okay, in Python. Okay. So let's see how to use this. So we have a lexer object, which we need to create, and then we had to call the tokens, right? So here's the main program. From lexer, import everything. Okay, and also this main program will import token types. Why? Because we want to check for end of file so that we can stop processing. Okay, so and then that's just a few lines of code. In this case, I put this in as a constant here, input equals that, but you'll see that when we run the program, I modified this so we can actually take the input from a command line. Okay. Anyway, no matter how you got the input, the lexer object is created by constructing the lexer object from the class, and it does require one string input s. Remember that, s? So that's what we provide here as the actual parameter. Okay, and then I print a message saying we are starting to tokenizing. Oh, by the way, this is the way in Python to do. It took me a while to figure this out. Okay, to do a print and not a print line. Okay, so basically tokenizing. I do want to print the input next to it. You see, so this is one way. Of course, you could have just said comma input, then whole thing will come in one line. Okay, but I think I put it here just so that there's in certain situations you may want to do this. Okay. Tokenizing, and then it prints the input. Okay, so when you'll see when we run the program. So it just prints this particular string. Okay, and after that it goes to a while true loop, and it gets the next token using the lexer.lex. Okay, so here the lexer object was created. Okay, when we provide the string. So as soon as this was created, automatically this was already tokenized internally. Okay, it doesn't return, and it just returns the object. But then when you call the lex method, you get one token after another. Okay. So t equals lexer.lex, and if t.getToken.value equals token types double equals token types.eof.value, this is how you check whether the 2 tokens are the same. And in this case, EOF, that means that we've reached the last token, right? So you break out of the while loop and stop. Okay, so that's the code here, and This is what the output you'll see, but let's go ahead and run it on the terminal to see this, okay? And I think I want to copy this guy here. Yeah, this part. Okay, I just want to show, see Lexer test, right? So this is the main program, and I did read it from, so you can see that there's a change here. I've commented that first line out. I put a comment, and I'm reading it from command line, sys.argv sub 1, okay? So that'll be whatever is typed next to the command when you run this program, okay? Sys.argv sub 1, okay? And the rest of the code is the same, I think so. Okay, so now it's ready to run. Okay, if you want quickly just to see Lexer py. Okay, so it's the same program. Okay, exactly same program. Okay, and the tokens and the token types also the same. Okay, so we are ready to run Python 3 Lexer test. Okay, and then this is where we give the string. Okay, yeah, this one. I got a very long folder name or directory name. That's why. Let's see. Yeah, I think now this looks a little better. Okay. So you can see that the command is, of course, you're running a Python program, Lexer test.py, and then this is sub 1, sys.argv sub 1, this part here as a string. The reason I had to put double quotes is because of the spaces. Otherwise, it'll treat white spaces as separator. Okay. And when I hit enter, you can see that it prints tokenizing this part, okay, that's we just saw, and then after that it prints all the token. Next token is, and the first one is lparen, okay, which is correct. The next one is ID, and its value is sum. You can see that the lex, so it gives a token type, and also gives the lexeme, the sum, okay. So that's the sum after the left, and then there should be a plus, which is the add token, okay. Then there's an int token, 47. Then there's a rparent token, which is the right parenthesis, and then there's a divide token, which is the slash, and then the ID token, which is the total, and then the EOF token, which is the -1. Okay, got it? So the tokenizing has happened properly. Now let's say that we run the same program, and let's say we make a mistake. Let's see what type of mistakes. Now this would be, not be a tokenizing mistake. It'll still do it, but you know that the balance parenthesis, the right parenthesis is missing. That's a job for the parser. Okay, so that's why it won't be detected here. Okay, so let's go ahead and put a comma here at the end. Okay, so you can see that it says unexpected character encountered, comma. Okay, got it? So I think it's working as expected. Okay, pretty straightforward program. But the point is that it's a systematic program. It follows the steps or the states and the steps in the state diagram. Okay, got it? All right. I don't know. I think this summer I'm not sure, but usually when I teach this class, I give a I like to give lots of programming assignments. Okay, so I usually give a define a language and ask you to build a lexical analyzer from scratch like this. Okay, it's not too big a deal. Okay, so it should be able to do it. So if I do give that program this summer as an homework, you should be able to do it. Okay. Anyway, we'll worry about that later. Okay, I don't know what type of assignments I'm going to give. Okay, but now we switch to the topic of parsing. Okay. Which is the syntax analysis, the second part, right? The first part is the lexical analysis, and then the syntax analysis. Syntax analysis or parsing is it deals with recognizing token sequence. Okay, that is the order in which the tokens appear. Okay, that's the main job. Okay, tokens is built from by the lexical analyzer, and then whenever you need a next token, you can call the lex method. Okay. But now parsers, okay. So far we have learned how at a high level how parsers sort of work. Okay, that is they take a grammar and then somehow magically they verify whether there is a derivation. Okay, for the string or for the program you're giving as input. Okay, now we are going to look into that magic or into the algorithms which go about doing this. Okay, so that's the part covered in this chapter or in this section of the course. Okay, so we are learning the nuts and bolts of the parsing algorithm, the lexical analysis, and so on. Okay, maybe not all the way fully, because we learned all the way fully in the compilers class. Okay, so this section is a mini compilers section. Okay, this actually even the previous chapter 3 and 4 are mini compiler. So it gives you a flavor of syntax analysis, the early stages of a compiler. Okay. Okay, so now we are getting into parsing. Okay, syntax analysis or parsing. These are two words or two phrases we use to refer to the same thing. Okay, syntax analysis is often referred to as parsing. And what does it do? A parser checks to see if the input program is syntactically correct, and if it determines that it is correct, then it constructs a parse tree. Okay, in the process while doing it. And if an error is found, a parser must produce a diagnostic message and try to recover, in the sense that it should try to skip over. So suppose at some a token it finds an unexpected token, then compiler should not stop there and give you the error, which is fine, but compiler should give you as many errors as possible. So what it will do is the compiler or the parser will try to recover from this and skip a couple of tokens until it finds a token where things can restart, you see? And then it will go try to do the syntax analysis from that point on. Okay, and again it might encounter error, and again it might try to recover. So in general, that's what the parser. We won't get into those details because those are covered in the compilers class. But at least certainly at the minimum, we must give a diagnostic message saying that there's a syntax error and this is possibly the cause. Okay. Yeah, and the reason recovery is required is because then the compiler can find as many errors as possible in one shot. Okay, that's useful. Otherwise, suppose you had 100 errors, let's say, in your program. Okay, then if the compiler reported only the first one, then you fix that, then you go back, there's 99 more, and sometimes when you fix one error, another 20 errors creep up, okay, because of that fix. Okay, whatever it is, then it gets very frustrating for the programmer, right, who is compiling the programs. So that's why one of the requirements of any compiler is to report as many errors as possible in one shot. Okay, all right. Anyway, those are general points. Now let's look at the categories of parsers. Okay, there are two main categories. One is referred to as a top-down parser, and the other one is a bottom-up parser. Okay, and they're distinguished based on the how they construct the parse tree. Okay, the order in which they construct the parse tree. Now, there's a parse tree. It's a tree, obviously, and we've seen examples of that before. Okay. There are two ways to construct the parse tree. You can start with the root node, construct that, and then construct the children nodes, which is it's called the expanding the node, and that's how we have learned it. Okay, actually we have not learned how to construct the bottom-up parse tree. Okay, in all the examples we did in the previous section, we constructed parse tree top-down. Okay, so this method probably is much more familiar to you, the top-down. Okay. So that is, you start with the root node, construct it, and then see how to expand it. And once you know which rule to use to expand, then you know the children nodes. So you construct the child nodes and draw the lines. Okay, and then you pick one of the non-terminals in the child nodes, and then expand that, and then so on. Okay, so this is called the top-down building of the parse tree. You start from the root and start building it until you get all leaves. Okay. And this is probably the normal way. Okay, you start from the root and then go down. Okay, but the bottom-up parsers do something strange and backwards. Okay, this is very interesting. Okay, it looks like it's a foolish thing or a difficult thing to do. Okay, but you will see as we get deeper into this, the algorithms we are going to study, the bottom-up parsers are really powerful. Okay. They have more power than the top-down parsers. Top-down parsers will fail for certain grammars, you see, whereas bottom-up parsers will never fail. Okay, so that's so it's a very robust method. Also, a little seems counterintuitive. Okay, and actually it is counterintuitive. Okay, why would you construct the tree bottom-up? Okay, so leaves means the tokens, right? Now, of course, at least we have the tokens. The lexical analyzer will give you a list of tokens, right? Or at least on demand, the next token. Okay, so at least we have the leaves. Okay, in some sense we have the leaves. So maybe it makes sense to go backwards. Okay, because I guess you also have the root. So So you can start top down, right? And you have the leaves with you. You have the root with you, and you have the leaves with you. What is the root? Root is the start node, okay? Start non-terminal node, okay? And what are the leaves? They are the tokens of the program which you're trying to parse, right? So actually, you do have the root and the leaves with you to begin with. And now your choice. Where do you want to begin? Do you want to begin with the root and then go down, which seems intuitive? Or do you want to start with the leaves and go up the tree and build the parent and build the parent until you get the root node, okay? Which seems counterintuitive, but the method we're going to learn, methods, well, I guess we'll see only one method, but there are many methods, okay, to build the bottom-up parsers. And the method we will learn at the end of this particular chapter, not this chapter, but yeah, that's right, this chapter, but it's the end of the next set of slides, which we will soon get to, okay? All right, so parsers are categorized into those two categories, okay? Now let's, before we actually get, oh, by the way, we will do top-down parsers first, okay? I guess the rest of the slides in this slide deck is all top-down, okay? But maybe there's one slide for bottom-up just to give you an idea of how it works, okay? In any case, in both top-down and bottom-up parsers, since we're going to deal with symbols, and terminals and non-terminals and mixed symbols, which is the right-hand side of rules and so on, it's a good idea to follow some conventions, okay, notational convention. And this slide talks about that, okay. So for this discussion, okay, for PLY and all is probably different, okay, but for this discussion, for the rest of the discussion in this whole chapter, okay, we're going to use this convention. All right, terminal symbols, if you want to represent terminal symbols, we'll use lowercase letters A, B, C, D, A, B, C, like that, okay? And for non-terminals, we'll use uppercase letters, okay? Which is just the opposite of what we recommend in PLY, okay? Correct? So don't worry about that. In theory, we do it this way, okay? And suppose you want to represent a string which is made up of mixed terminals and non-terminals, okay? Mix of these two. Of course, you can use those letters combined like in the string, but if you want only one symbol, then we will use the letters W, X, Y, Z, capital, all caps, okay? For a mix of terminal and non-terminal symbols. But if it's just a string of terminals, okay, by the way, the first three are all single letter notations, okay? But this one also is a single letter notation, but it denotes a string of terminals, okay? So if you want to denote a long string of terminals, we'll refer to them with lowercase w, x, y, z, towards the end of the alphabet, okay? And of course, if you had a long string made up of terminals and non-terminals, then we will use the alpha, beta, gamma, delta from Greek, okay? Greek letters. All right, so pay attention to these when we write some X, Y, Z, W, Q, V, alpha, beta in the subsequent slides, okay? You must remember what they are, okay? Got it? I think the terminals, non-terminals, and the Greek are easy to sort of memorize. This one, sometimes you may get confused. This is the terminals and non-terminals. Single letters, okay? So the first three are for single letters here, single letter symbols, okay? And then this is also single letter symbols, but they denote longer strings of terminals, okay? And then the mixed string of terminals is here, okay? Okay. So actually there are 4 slides, yeah, that's right. Okay, 4 slides which sort of summarize 2 for top down and 2 for bottom up, okay? So the top down has got 2 slides here. Will give you a general idea of this parsing method, okay? And same with the bottom up, the 2 slides here, okay? And then we will get into the depth of the top down and the bottom up, okay? So this is just a very high level view of the top down parser, okay? Like we said, a top down parser traces or builds the parse tree in, oh, we didn't say pre-order, but that's what it does, okay? It visits each node before its branches are followed, and that's typically the pre-order, right? And the second observation is the top-down methods they always follow the leftmost derivation method. You see, that is the way you expand the non-terminals would be you choose the leftmost always, okay? it follows the same pattern as the pre-order, so that's why okay. So we'll be expanding the leftmost non-terminal available. Okay, and then let's say that currently this is the sentential form in the leftmost derivation. Okay, you remember sentential form is any string in the derivation, right? At any step. So let's say that this is how this is x a alpha. Okay, so that this thing is an alpha here. Okay, not an a. Yeah, maybe I can. I remember when I was. Does that look? Yeah, it does look the same as this. Anyway, that's an alpha. I'll try to typeset this so that this looks a little bit more like an alpha. Okay. I will try to fix this in the slides. Okay, but anyway, x a alpha. Okay, let's say this is the sentential form. Now you have to pay attention to the letters here. X is lowercase x, which means it's a bunch of terminals. This is a bunch of terminal tokens. X is a bunch of tokens. Okay, and a is a non-terminal, right? Yeah, that's a symbol. And then alpha is this is alpha, so it's a Greek letter. So which means it's a bunch of terminal and non-terminals. Okay, mixed. Got it? So that's why we talked about the special conventions, so that we know exactly what this is made up of. So this string, another way to say this is that a is the first non-terminal in this string, leftmost non-terminal, right? Because everything to the left of a is x, which is all terminal symbols, which is tokens. So a must be the first non-terminal. Okay. And after that, we don't know what is there. Alpha is a mix of terminals and non-terminals. Suppose that's the sentential form we are looking at, okay, at this point. All right. Then, because we are trying to imitate a leftmost derivation, then we must find a rule for a, correct? A grammar rule for a, so that we can expand this a, okay? Because it's time to expand a, okay, or replace a by the right-hand side of the rule, okay? Got it? And then you get the next sentential form out of that. So that's what the task is. A top-down parser's task is to find the next sentential form in the leftmost derivation. And in particular, it must determine which correct grammar rule, which has a in the left-hand side, we must use. Okay, so we must determining the next sentential form is a matter of choosing the correct grammar rule that has a as the left-hand side. Correct? Because now it's time to expand a in the leftmost derivation, and that's why we must make the right choice here. Okay. Of course, if there's only one rule for a, perfect. You don't have to make a choice. You just use that. Okay. But if there are multiple rules, or if there are no rules for a, then there's a disaster. Something wrong in the grammar. Okay. But if there are multiple choices, then we have to choose the right one. Okay. And the question is how to choose that. Okay. Because it seems non-deterministic, right? Again, we won't get into the depth of this at this point. We will when we look at more detailed. Okay, but let's say in these two slides when we're discussing, let's say that these are the three rules we have. This is just again an example. Okay, correct. So a replaced by, oh, by the way, this arrow is the same as a colon. Okay, b, small b, capital B, or a replaced by small c, capital B, small b. Okay, small c and small b are the terminals, and b, capital B is a non-terminal, and a is little a. Okay, so here we have three choices. Okay, now if this is the only thing given to you, then there's no way to figure out which one you can use any one of them, right? All right, but anyway, suppose let's look at all the three cases. If you use the first case, then this is the next sentential form, correct? Because you have replaced x a in x a alpha by x bb alpha. Okay, so that's the replacement. A has been replaced by bb. Or if you use the second rule, this is what you'll get. Okay, or if you use the third rule, this is what you'd get. Okay, so we have the three possibilities for the next sentential form, assuming these are the only three rules. Okay, and assuming this is given to us x a a. Okay, so under all these conditions, there are three possibilities for the next sentential form. Okay, so the question is which one will it be? Okay. And that must be built into the part of the algorithm, right, to decide which one to choose. Okay, and this can be decided based, and here the last comment talks about it. Okay, the most common used top-down methods, algorithms, choose an A rule based on the token that would be first generated by A. Okay, so you can see that in all of these, if you use the first rule, A will generate the B token, right? And then in this, A will generate the C token. In this, A will generate the A token. So we need to figure out, starting from A, if A was given as a start symbol, okay? Considering all possibilities for all replacements of derivations starting from A up to what token can show up in the front? That's really the question, okay? And that's what this says. And if we can figure that out, okay, which token will be first generated by A, then we can choose the rule, because we know the input is given to us, okay? So we can actually scan the input, and in particular the next token, the Lex, we can ask Lex for the next token, okay, right? And Lex will tell us, oh, this is the next token. And if that matches, let's say C, okay, then we know that this is the rule to use, okay? And if that matches A, then we know this is the rule to use. And if that matches B, then this is the rule to use. And that matches none of these three, then we know there is no parse available, okay? Then there's a syntax error, okay? Got it? So really the whole thing boils down. So there is a decision point in the algorithm, in the top-down algorithm, which rule to use. And I think we asked this question earlier too, right? When we talked about derivations and so on, okay? And now we are ready to answer that question, not fully, but close to, okay? And that is, we can get the next token from the Lexer, and then we can look at because it's time to expand A at this point, okay? Right? So we can look at A as, assume A is the start symbol. It is not, but suppose it is, okay? Then you look at all possible strings which can be generated from A, and look at the beginning, the first target, first token in those strings, okay? And find a set. And that is actually an algorithm for that, and actually we will probably look at it later, okay? And look at that set, and also see if the rule, if there's a unique rule, which of course you have to see whether that one matches the next token, okay? So the next token, if it is one of the tokens generated from A as the first token, okay, then you see if there's a rule which has that in the beginning, okay, and you use that rule, okay. So this is how you make a decision at this point, okay. Anyway, we'll get to the details later, okay. But that's this last point basically reveals the secret behind the top-down method, okay. All right. Now let's go ahead and look at the methods for the top-down. Okay, there are two general methods. One is called the recursive descent parser. Okay, and that's what we will look at more detail. Okay, the second one is a parsing table rather than actually a code. Okay, so there's a parsing table method for generating the top-down parse tree. Okay, got it. And in this class, I think we discuss recursive descent a little in depth with an example, but we skip over the parsing table method for top-down parsers, okay? And since we're going to get into the depth of recursive descent, so we're going to just give it a name right now, and then we'll talk about it when we get to the slide, okay? Now, just two more points, or one more point, okay? Both these algorithms, the recursive descent and the parsing, are referred to as an LL algorithm, okay? The first L in the LL refers to the left to right scan of the input, but that's common always, okay? So first L will be left to right scan of the input, okay? We don't scan the input right to left, okay? But the second L specifies that it generates a parse tree using the leftmost derivation, okay? And that's why this class of algorithms is called the LL algorithms, okay? So under this category of LL algorithms, you'll find top-down algorithms, and a couple of them are available. One is called the recursive descent, and the other one is called parsing table method, okay? So, but anyway, the category of top-down algorithms is called LL algorithms, okay? Because all top-down methods or all top-down algorithms will do a left-to-right scan of the input, and also will derive the parse tree using the leftmost derivation, okay? All right, so we are going to look at a handwritten recursive descent parser later in this chapter, okay, or in this section, okay. So this part we will do in more depth, but we will not do this, okay. So those are just the basic introduction to the top-down method, and again a very basic introduction to the bottom-up in the next 2 slides. Okay, and then we can get to the details. Okay, so the bottom-up, like I said, is a little counterintuitive. Okay, the bottom-up parsing method in general. Okay, it starts at the leaves. Okay, so backwards. Okay, and then it progresses towards the root. That makes sense. Okay, so you start with the leaves. Leaves are all given to us, by the way. Okay, that's what the lexical analyzer does for us. Okay, and so that's, you start with the leaves and then go and then find the parents of a bunch of leaves and then put the parent, and then find the parent of a bunch of not necessarily leaves anymore, but the internal nodes and the leaves. Or in some sense, you can think of these as, you could treat each of the tokens as a root by itself. Okay, and then what each step does is that it combines the roots of the existing trees, some, not all, some of them as children, and creates a new root. Okay, got it? So at any point in time, you have a bunch of roots of trees. Okay, initially they're all just single node roots. Okay, and then you're combining nodes together. Okay, as children of a particular new node, internal node, and you create that and then construct the tree for that. Okay, and you keep doing this until all the nodes vanish, root nodes vanish, and you're left with only one root node, which is the root of the full parse tree. Okay, we got about 5-6 minutes, so hopefully we can discuss these 2 slides. Okay, yeah, just the gist of how this works. Okay. All right, so because we are following the rightmost derivation, okay. Oh, by the way, the parse tree also corresponds to the reverse of the rightmost derivation. Okay, got it? So this is why I said this whole method is counterintuitive. First of all, it's almost like running a marathon backwards. Okay, you're facing one way, but you're running the other way. Okay, so that's what this looks like. Okay. All right, we are trying to generate the rightmost derivation, but not in the proper order, but backwards. Okay, so we start with the final string and then the previous one to previous one until the first one. Okay, the first string should be the start symbol, right? So that's important reverse. Okay, so given a right sentential form, again, this alpha doesn't look like an alpha, it looks like an A. I'll try to fix this, okay, so that when you see the slides, you'll see a better alpha there. Okay. Given right sentential form at any point in time, okay, so, and typically this would be the last one, the full terminal string. Okay, a bottom-up parser must determine what substring of alpha. Okay, by the way, alpha can contain terminals and non-terminals. That's why we chose alpha here. Okay, so we need to find a substring inside this. Okay, all right, but not any random substring. It should be a substring which matches the right-hand side of a rule. Okay. So it's backwards. So given a string, you want a substring which which is exactly the right hand side of a rule, okay, of a grammar rule. Okay, now you may have many right hand sides there, okay, right, but you want to find one, okay, and the correct one. Okay, so very much like in the top down, we had to choose the correct rule. Here we had to choose the correct substring. Okay. The choice is there, but you have to choose the right one. And if you do choose the right one, then this method will work. Okay, got it? So we are looking at substrings of the given string, the sentential form alpha. We look at a substring, more than one possibly, some substrings which are right-hand sides of rules. Okay, all right. This may not be too difficult a task if you're just given a programming task, right? Because you look at, let's say, all the right-hand sides. Okay. All you'll do is you'll take the right-hand side of a rule and you'll say if index of, okay, or dot substring will give true or false, right? So every programming language has a method to check for substring, right? So that you can use that, okay, and then you can find all the possible right-hand sides in the current string, okay. But we want to pick the right one, right? So that's the difficult part, okay. All right. Anyway, that's really what we had to do. And suppose you do find the right one, then what we do is we replace that substring by the left-hand side of the rule, okay? Because you're going backwards, right? In the forward method, we are replacing the left-hand side by the right-hand side. In the backward method, we'll replace the right-hand side by the left-hand side. That's all, okay? And this process of replacing right-hand side by left-hand side is called reduction or reduced, okay? So that's what we'll have to do, okay? But the only key question to answer left is how do you find the right one, okay? The right substring. And here's a tiny discussion on that. Given a right sentential form, which may include more than one right-hand side from the grammar, right? That's possible. The correct right-hand side to reduce is given a name, and it's called the handle. Okay, what is a handle? It is one amongst the many right-hand sides which is available in the right sentential form right now. Okay, one, and actually there's a theorem which says that there's exactly one handle. Okay, which so that's the theory behind this whole method. So it's backed by theory, solid theory. Okay, so here's a quick example. Okay, suppose you had these three rules: S is AAC, A is AA, and A is B. Okay, A goes to B. Okay, so these are the three rules in the grammar. Okay, and here's a rightmost derivation for AABC. Okay, let's say this is the final terminal string AABC. Okay, this is you start with S, and then you go here, and then go here, and go here. Okay, in 3 steps you can derive that. Okay, you can look at it. Okay, now I've copied it twice. Okay, and the same derivation I copied it twice. Okay. Now, and since we're going backwards, we'll start at this point, right? So we'll, in both the cases, or we'll start. Don't worry about why there are 2 here. Let's just look at the first one, okay? We start with AABC, right? So that's our current sentential form. Now, these are the only 3 right-hand sides, AAC, AA, and B. These are the 3 right-hand sides given to us, okay? So the question is, in this string AABC, which of these right-hand sides appear as a substring? That's a question. And the answer is not too difficult. Answer is only this one appears, this B, correct? Only B appears as a right-hand side. Little a, capital A does not appear here. Little a, and then little a, capital A, little c does not appear here. And the main reason is because no capital A appears in this, right? So when you start at this sentential form, it's easy to determine what the previous step should be. It should be this guy. This rule should have been used, right? Why? Because we're going backwards. So we'll replace this B, which is the right-hand side, by the A, capital A. So that's how you get this string, okay? In both these derivations. The reason we show both derivations, it's the same derivation, but we show it twice, is because in the next step, you'll see there'll be a choice, okay? And that's why I wanted to show this twice. But okay, so reaching this point is no problem. All of us agree we can do it deterministically. We can go from this to this because there's only one right-hand side here, okay? And that is the handle. So this part is called the handle, the B, okay? And we replace it with the left-hand side, which is the A, okay? Now, if you look at this, little a, capital A, C, and ask the same question, how many right-hand sides are here? Then you will see that there are 2 of them, okay? This B is not there anymore, right? So in this B doesn't appear, so that right-hand side is not there. But if you look at the other 2 right-hand sides, they're there, okay? You can see that one is this AAC, which is the last 3 symbols, okay? AAC is there. Also, this AA is there. Actually, here, so I can show you, it's here, okay? And that's the reason I showed it in 2 lines, so you can actually highlight and see that, okay? So now there's a problem, right? So because right now we have a working string or the right sentential form, which has not 2 handles, but it's got 2 right-hand sides, and we have to choose which is the right handle, okay? And this becomes difficult, okay? And actually we will see how this is handled later on. But I just wanted to alert you to the method and how this works, okay? Okay, I think we stop here, and we continue from this on the next video.